All right, welcome back, folks. And today we're gonna finally wrap up our discussion of threads. This is gonna be the last lecture on concepts of threads in general. We still have 2 more lectures on concurrency where we're gonna talk about deadlocks, but we're not gonna be going into, we're not gonna be bringing up the theoretical threads until later. A few announcements before we get started. There is no activity associated with the session today, so you only have the Clear-Muddy survey to do after the session. Remember that the Advanced Semaphores Lab is due tonight, so even if you're not planning on submitting this one, please make sure you do it before exam 2. Okay, it's very important that you do that before exam 2. I'm going to give you a little bit more hints in the next slide. And recall that project milestone 2 is due on Monday. Tomorrow we're going to have a work time, but I'm going to force you to actually get started on the milestone. So come prepared to do that. Okay. Exam 2 announcements. So it's going to be next Friday, 6 to 9 p.m. It's not the best thing in the world, but given a few things, we're probably going to have to do it this way. It's going to be threads and semaphores, so no scheduling, no file system management. If you do have a conflict, then please let me know. I know a couple of you have already emailed me, and I'll try to find a solution that works for everyone. Okay, but please email me early so I can find a solution that works for you. This is very important. So for the exam, focus on the following. In the readers and writers problem, focus on both the behaviors of the readers and the behaviors of the writers. So how did we allow multiple readers to go in at the same time? And how did we coordinate that if the first reader comes in, they post a sign to block the writers from coming in? So remember those techniques because you're going to need them. Second thing we did is we solved the issue of non-starving writers. So we added one more semaphore to act as a lock to prevent new readers from coming in. So again, keep that in mind. You're going to need those techniques. So make sure you study up on them, you review them, you implement them a few times just to get them in your head. From today's homework, there's a file called band.c. Make sure you know how to implement this file. Know how to implement the problem in this one. Okay? So even if you're not submitting the advanced homework, please do this one. You're going to need it on the exam as well. So exam structure is one p-thread problem where you just have to create threads and do stuff with them, pass arguments, and do all of that small nitpicky stuff. 3 problems on semaphores, and I have 3 techniques for you here. So make sure that you study up on those and use that information as you see fit. Okay? Questions? Yeah.
Conditional stuff, none of that, no new text.
No, so you can solve the entire problem, the entire exam, you can solve it using semaphores. Sometimes if you think that the condition variable is going to help you more than a semaphore, you can use that, but it's designed to be solved entirely using semaphores. Yeah. Yes?
Have you decided if it's in person yet or?
I'll probably let you know by Monday. Yeah. Yeah.
Will this one also have the makeup hang with the last?
Yes. Yeah, there will be a makeup a week after. Okay. Other questions? All right, good. So let's wrap up our discussion of threads by remembering what threads are. So if you recall this diagram from before, we said that this is a single process. And a single process is comprised of several memory regions. Those are the code, data, heap, and the stack. And when we introduced the concept of a thread, we said that threads share share the code, the data, and the heap, but they have separate stacks and registers. So those are their own. So stack is their own stack. Registers are their own kind of state of the CPU that they left when they were doing their business, right? We said those are like lighter weight processes because they share this memory address. So we can do multi-processing in a more lightweight way. They share the code, data, and heap, but have their own separate stacks, registers, and program. So now the question we want to answer today in class, if you recall this diagram that we built before, we had the hardware at the bottom level. We had a bunch of device drivers here. So these are device drivers. And we had the core kernel capabilities like process management, memory management, and so on. This is the kernel. And on top of that, we had user space. And this is where we have our applications and their multiple threads. So now the question is that we want to answer is who manages threads? So that's what we want to answer in today's class. And we're going to use today's class as leading towards your next advanced lab, which is going to be implementing a version of thread management that we're going to discuss at the end of the lecture. That will be due on the Monday after your exam. All right, so not Thursday before the exam. It's going to be due the first Monday after we do our exam. So who are the candidates for managing the threads? If we look at this picture and this separation of functionality, what are the candidates of who's going to take care of managing those threads for us? And try to remember what you kind of a little bit of what you did in user space lab 1 and 2. Yeah. Okay, so one possibility, I'm going to leave a little bit of room here. Possibility is that the kernel manages the threads. Okay, in our first 2 labs, who was managing the threads? Who was scheduling the threads? Who was swapping the contexts? Yep. Yep, so another place to do that is we do that totally in user space. Okay, and as every problem in computer science, you can always do both. Right, there's one solution, there's the second solution, and there's the one that brings the two together. So what you're going to do in your next advanced lab is the one that does both. But we'll talk about that today. So let's start with discussing user space threads. So I like to think of this as basically the process comes in, tells the operating system like, hey, I'm a strong independent process. If I have threads, I'm the one who's going to take care of them, right? I do not need any help from you. You should not be aware of my threads, my kids. That's all my responsibility to do that. So if we want to draw this, this is the kernel in here. This is user space. This is our process. And then the threads in here are all managed by the process. So the OS is not responsible for doing anything when it comes to those threads. So what do we mean by managing a thread or managing threads? There are several things. One is creating the threads. Second thing is doing context switching. And the third one is doing the schedule. So when we say that everything is managed in user space, this means that the process itself creates its children. The process itself changes its children, swaps between one or the other, and the user space is the only one who's going to schedule how the children execute. So do you remember from the first two labs what APIs we used to do these things? Yep. Yep, we used uContext T, and we said this represents a thread. And then we said that this creating a thread, we used make context, context switching. We said that I think it was swap context. And for scheduling, we did timers plus scheduler that uses swap context, right? So that's effectively eventually what we ended up with. User space lab was just executing things in a first in, first out fashion until they're completely done. Each thread is completely done. But then after that, we added the capability of setting up an alarm and then swapping the force swapping from one thread to the other. So now the question I want to ask you is, from the point of view of the kernel, what does it see? Is it going to see multiple threads, or is it going to see a single process? Yeah.
Like just one application trying to do one single process and using all of the space.
Yes, exactly. So the kernel, in this case, sees a unique or only one process. So the kernel, in a sense, is not aware of the threads, of the existence of those threads. Okay? So do you think there's, let's do, so the kernel only sees one thing in here, right? And what the kernel is actually doing is creating this mapping between all of these into just one entity in the kernel. So we refer as this to the entity that they map to as a kernel thread. And that executes on behalf of just one process. So it only sees one thing executing, not many things executing. So in thinking back to our figure here and the roles that the operating system plays, what do you think are the problems that might arise if the kernel only sees the thread, does not sees the one process, it does not see its child threads? What could be the problems that arise in that case? Yep. Can you say that?
The other threads could run indefinitely.
So the other threads could run indefinitely. What do you mean by running indefinitely? Okay, so there is kind of like a difference that might happen between how the threads run effectively, right? So I think to build on top of that, at any point in time, how many of those threads can they be running at the same time? So the mapping is many processes in here to, or many threads in here to one kernel thread. Yeah.
Only one can be running at a time, running at a time because it can only see one. So.
Yeah, exactly. So the main problem in this case is that the operating system only sees one thread, or one main thread, one process. So when it tries to execute that, it's only going to execute it on one CPU. If I have 20 CPUs and all other 19 are empty, I'm only going to run on one of those because I only see one process. I'm not aware of the existence of those threads in there. So as an operating system, I only see one process, I run one process. The fact that that process contains multiple threads is not up to, is not my job in a sense, right? You chose to do that to yourself, you live with it, right? You can't really ask me to jump into your code and see that you're running multiple threads and then figure out that you want multiple CPUs. So that's not the job of the operating system. Yeah.
Or multiple CPUs, are you referring to multiple physical CPUs and multiple cores?
Both work. Yeah. So even multiple cores or physical CPUs or hyper-threading, whatever you want to call it, effectively, even if you have all of those technologies together, you have two processors, each has 4 cores with hyper-threading on top of them, you're only going to run on one logical thread. Okay. Right? So let's start thinking about these problems. So first thing is that there's no parallelism. So which beats the purpose of using threads, right? So why do you even use threads if you're not going to end up using multiple processors? You're not going to be doing things in parallel. Another problem that we might think of is, well, let's say one of your threads, so one of these threads, let's say this one in here, blocks for I/O. What happens to the entire process? So it issued a request to read things from disk, and it's going to take 20 seconds to read things from disk at that point in time. What happens to the entire process at that point in time? Can we execute another thread?
Is it not unless you like specifically program it to detect your program to detect that?
Yeah. So unless I specifically program my threads to, if they issue a read from disk request, they're going to swap things around and run another one. The entire process is going to block. Even if it's just one thread that issued the reading request, that thread is going to block the entire process. So the problem is if one thread blocks, then the entire process blocks. Entire process blocks. Okay. Questions? All right. So, but we have been like kind of attacking kernel user space threads so far. So maybe it's time to kind of like just think of any advantages of doing this. Are there any advantages of us doing user space threads? What are the benefits of doing that? Yeah.
I guess since you're handling like the switching yourselves, you don't have to worry about race conditions.
Yeah. So since there's no parallelism, there's no need to worry about concurrency. Right? unless you wrote a really bad scheduler that swaps things out at very weird moments, at most, one thing will be running at a time. So your worries about concurrency become relaxed more, right? You don't have to worry about it as much as you're thinking about an adversary. You're thinking about the scheduler as your adversary that's going to swap you out at the worst possible moment. You decide when things swap out, so you decide how things happen, right? So this leads us to kind of along those lines. It gives you full control over scheduling. And you can even do multiple policies within the same process. So if I want a subset of my tasks to be doing first in, first out, another subset of my tasks to be doing priority queuing, another subset to be doing round robin, I have full control to do that. I don't have to, live off someone else's favor that they're scheduling my threads. I take care of everything, and I just do whatever I want with those. The third benefit of these is that we're going to have lightweight switching, context switching. So if the OS is not aware of my threads, whenever I want to do a context switch on my threads, I don't have to involve the operating system in that. So I can do that on the fly, right? It's going to be much, much faster, and I have to go to the operating system, swap myself out to get the OS to execute on my behalf. The OS is going to do something, it's going to return to me, and it's going to actually execute another thread. That's a lot of time and a lot of communication wasted. What I can do in user space threads, I have control over my threads. If I want to swap them, I just do it on the fly. So I don't have to worry too much about the overhead. So we call this like a low overhead of context switching. Okay. So nowadays, it's very unlikely that you're going to see an implementation of threading fully in user space. But in the Linux kernel, the last support for those was called in green threads. It was Linux version 2.6. Now we are Linux version 5.11. And since 2.6, we have dropped those user space threads, right? Because there's no point in doing that if we're running on an 8-core CPU and we can only run the process on one of those, right? So you can still write your own library if you'd like to, but there's no defaults that are given to you by Linux. Okay, so now that we have done the first step, which is the process is kind of like a helicopter parent over its children. It controls everything when they're born, when they die, whatever, all of the other things. We're going to go to the exact opposite. What the process is going to do is going to call the OS and tell him, hey, I want 5 children. You do whatever you want with them. I just want to play with them. So I just want them to execute these things. I don't care when you schedule them. I don't care when if you do some weird things to them. I just want them to execute these pieces of code, and you handle everything else. You're kind of like the opposite, very, very lazy parent, in a sense, right? So in this case, we're just going to call on the OS and ask the OS to handle everything. So this now becomes kernel level threads. So in this case, recall what we did in pthread create. We just passed the thread itself in here. So it's like pthread underscore t. The second parameter was 0. Third parameter was the function to run. And last parameter was the argument. And that's it. We just asked the operating system, create this thread for me, and I want this thread to execute this function. Go. I don't care about how you schedule them. Whatever scheduling algorithm you're doing, it's totally up to you. All right. So what happens here is that the OS handles thread creation. The OS handles context switching. And the OS handles scheduling. Okay. So because of this now, if I have multiple CPUs, then the OS can schedule different threads on different CPUs. So we got around the problem of underutilizing our resources. Now, if the kernel knows we have 8 cores and I have 8 processes or 8 threads, the kernel is going to run those threads for me on those 8 cores, assuming I'm the only one. Right? So we got back our parallelism benefits. Now, the other thing that we got, so this is 1. The other thing that we got back, if one thread blocks, then it's not necessary that the other threads are going to block as well, right? So then other threads can still run. So how does that happen from the kernel's point of view? This is kernel space. This is user space. And the way things happen is if a process in here creates 3 threads, what the kernel is going to do, it's going to create a kernel thread for each one of those. So user thread has a corresponding kernel thread. So we said before we had the many-to-one model. This is the one-to-one model of thread management. Okay, so if we recall from our previous, like around the first few times we discussed processes and threads, we said that the Linux kernel maintains a PCB for each thread. Each process and each thread has its own task structure, right? So in the case of user space threads, how many task structures do we have? How many PCBs do we have? Just one, right? So we only have one PCB. Now, in the one-to-one case, if I call pthread create 4 times, how many PCBs do I have? Yeah. Yeah, exactly. Yeah, so you have 5 PCBs. So if I call pthread create 4 times, then I end up with 5 PCBs. That's in the Linux kernel. So don't forget about your main thread always, and make sure you're doing the right thing. So we talked about the advantages of using, of getting the one-to-one models. What are the disadvantages of using it? So can you think of any disadvantages compared to the many-to-one model that we talked about before?
Control.
Yeah, so first thing is you have much less control. So whatever the OS decides to use as a scheduling policy, you are stuck with that. You cannot use another scheduling policy, right? You cannot ask the OS like, hey, I want these to do round robin and these to do first in, first out, and these to do MLF queues, right? You cannot do that. Whatever the OS decides to do, you're just stuck with it, right? So we have less control over scheduling. What are the other, what other disadvantage you can think of? So if you want to look back to the advantages of yeah.
Every wave context switching.
Yeah. So since we're doing lighter context switching, we have more overhead to do context switching. Because each and every context switch now has to involve the operating system. In the first case, the context switches did not have to involve the operating system. Now, every single context switch that has to happen, the OS has to decide when it's going to happen, the OS has to do it, and then that results in more overhead to doing that. Okay? So a direct impact of number one is more concurrency issues. Because we have less control, then we have to worry about concurrency because we might be scheduled out at multiple times, or at the worst possible places. Questions? Okay, so now jump back to the slides. Okay, so what we're going to ask you to do in your next advanced lab is the following. You're going to combine the cheapness and the control of user space threads along with the power and parallelism of kernel threads. So normally we can do that. So we can do it. It's doable, but it's very complicated. And since it's complicated, we're going to ask you to implement, right? As is the trend in this class, right? The more complicated the thing is, the more we're going to ask you to do it. Applications of hybrid threads, or what we're going to call hybrid threads, which is a combination of user space threads and kernel threads, usually those are reserved for massively parallel systems. So the systems that requires thousands and thousands of threads. So one good example of that is a massive web server, right? If I'm getting 1 million requests from each user and I need 1 million threads to handle those, then just doing a one-to-one mapping is not going to cut it, right? I do have those things typically run on a massive data center, so we need a good mechanism that spreads those out consistently. And we use them is when we use kind of a combination between user space threads and kernel threads. So web services, there is, I think in Java you call it thread pool. If you did that in Java, there is an idea of a thread pool that is also a combination of both. And the way it's implemented is that we have a many-to-many model. So usually we refer to this as the M to N model, where M is typically much larger than N. Okay, so if we wanted to use the one-to-one model, so one-to-one, we're only bound to use n threads. If the kernel has only supports 10 threads at the same time, I cannot create more than 10 threads at the same time. When I do this mapping, I can map 100 threads to 10 kernel threads. So what I create is each 10 threads will map to one thread. The second set of 10 threads will map to one thread, and so on and so forth. So I can still run things in parallel. I can still have control over my scheduling, and at the same time, I get the benefits of doing things in kernel space. Okay? So that's what you're going to be implementing in the next advanced lab. For today, that's everything I had. Unless you have any other questions, feel free to hang around and ask questions about today's lab. We have about 15 minutes left, I think. Otherwise, you're also free to go if you're done with them.